So this is the practice test review for the stoichiometry test. A couple of the questions in this review video may have slight variations from the questions on your version of the test, depending on whether you're looking at the printed version or you printed out a version from online. In most cases, it's just that the answers are in a different order. There are one or two questions where the questions themselves are slightly different, but I'm going to show you how to solve each question based on what's on the screen, and then if there's a slight variation, you might get a slightly different answer, but you would solve it the same way, and the questions on the real test are going to be slightly different anyway. So it's all about how you would solve these types of questions. So the first question is a balancing question. If we balance this equation, what would the coefficients be? Well, the first thing you're going to want to look at is how many of each element are on both sides. We've got one lead, one sulfur, two oxygens on one side. We've got one lead, one sulfur, and three oxygens on the other. So the fact that I've got two oxygens on one side and three on the other, that's going to have to be fixed. Most likely what we're going to end up with is 6 on both sides, so that's kind of a good place to start. So if we put a 3 in front of that oxygen, and if we put a 2 in front of this oxygen and a 2 in front of that oxygen with the sulfur and lead as well, what we end up with is 6 oxygens on both sides. We end up with 2 leads and 2 sulfurs on this side. And then if we put a 2 in front of the lead and sulfur on that side, we end up with 2, 2, and 6, 2, 2, and 6. So that means the equation is balanced, and the answer here, the coefficients are 2, 3, 2, and 2. Same type of question, different equation. We've got the 1 carbon, 2 sulfurs, 2 oxygens on one side. On the other side, we've got 1 carbon, 1 sulfur, and 4 oxygens. Well, if we are going to have to change, the first thing is that the sulfurs don't balance, so we have to put a 2 in front of that. Gives us 2 sulfurs, but it now gives us 6 oxygens, which means I need 6 oxygens on the other side. If I put a 3 in front of this oxygen, it gives me 6. So my coefficients now are 1, 3, 1, and 2, which is this answer down here. Here's another balancing equation, and this is one where the answer you get might be slightly different depending on the version of the test that you're looking at. So I'm just going to go ahead and give you all of the coefficients for this equation. Okay, when you balance it out, what you end up with is coefficients of 2, 6, 10 on the left, and then 6, 10, and 1 on the right. Okay, so depending on what the question is asking you, you would find the appropriate. In this case, for example, it's asking for the coefficient of the the P4. In this case, the correct coefficient there would be 1. In other versions, it might be asking you about the CaSiO3, in which case it would be 6. But once you balance the equation, you would choose the appropriate coefficient there. Which of these equations is properly balanced? Well, we have to look for the one that's got the same thing on both sides. The first one has 2 chlorines and 2 hydrogens on this side and only 1 of each on the other side, so that's not it. This one's got 2 HCl and 1 magnesium. On this side it's got 4 H. On this side it's only got 2 H, so that's not the right one. This one's got 2 HCl. On the left it's got 2 H and 2 Cl, and it's got 1 magnesium. So the correct answer is this one. The last one has the wrong number of atoms on both sides. So answer choice 3 in this case. Again, it might be a different answer choice in your version, but it should be the same equation. Okay, same question. Which of the following is balanced? Well, if we look at the equation, the coefficients that we need end up being 2, 1, 3, and 4. You can see in the first one, it's 4 nitrogens on the left and only 2 on the right. This one, again, has more nitrogens on the left than the right. This one has more nitrogens on the left than the right. So even just by process of looking at the nitrogens, you can eliminate 3 out of the 4 choices, but just find the one that's balanced. How many moles are in 43.9 grams of water? You might have a different number for the number of grams in your version, but you would solve the question the exact same way no matter what. You take the amount that you're given and you divide it by the mass of water. H2O is 2 hydrogens and 1 oxygen with a mass of 16. The mass of water is 18. So we are going to have 43.9 divided by 18, and we get 2.44 moles. So again, no matter what number you have for the top, the bottom part of this is going to be the same, and you just divide the amount given by the molar mass to get the answer. Balancing equations are based on the law of conservation of mass and conservation of matter, which are essentially the same thing. They both say that atoms essentially are not created or destroyed during a reaction, which means same number of atoms is the same number of mass and the exact same amount of matter. So both of those rules apply to balancing equations. Okay, the net ionic equation. So again, this may be one where your version is different, might be the same, but the way you would go about solving this is the same no matter what version you have. You have to remember 3 rules for what is soluble and what is not soluble. So the first thing is any substance with an alkali metal is soluble, or with ammonium, which is NH4. Anything with those substances in it is always soluble. So if it's got sodium, lithium, potassium, or ammonium, the NH4, it's always aqueous. If it is a compound of nitrate, NO3, it's always aqueous. If it's a compound with chlorine, bromine, or iodine, that's aqueous, unless they are combined with silver, lead, or mercury. Okay, then they're not soluble. So alkali metals or ammonium, always aqueous. Nitrate, always aqueous. Chlorine, bromine, iodine, always aqueous unless they're with silver, lead, or mercury. Those are the ones that are always soluble. Everything else is not soluble. So when you're doing the net ionic equation like this, what you have to look at is, okay, so if I take Na3, ASO4, and CuSO4, and I do a double replacement reaction, what do I get? Well, I'm not balancing this right now, just to show you the combinations, NaSO4 and CuASO4. Okay, well, this has got sodium in it, which is an alkali metal, which is rule number 1 of solubility. That's not going to be a precipitate. The other one has copper, which is not mentioned anywhere in my solubility of always aqueous, and ASO4, which is not, it's arsenate, it's not mentioned in my solubility rules. So this is going to form a solid. Okay, that's a precipitate. If we looked at this equation and both substances were aqueous, then the answer would be no reaction. But that's not what we get. We get a solid with the CuASO4. So the net ionic reaction only has copper and arsenate in it, which means it's not this, it's not no reaction, because we do have something that's not soluble. So that leaves the last 2 choices here. The one that's correct is the one that's balanced. And if you look at the charges, we've got a +2 and a -3, which means it can't just be CuASO4, even though I did write it down here. I told you this wasn't balanced. So the charges don't match, which means it can't be a simple formula like that. That's not the right answer. This is the correct answer. It is balanced, and it has the right ions that form the precipitate. Which of the following is a combination reaction only? And combination is just another word for synthesis. So what we're looking for is reactions that have the general form A plus B becomes AB combined. So only one product on the right-hand side, which eliminates these two as possibilities and leaves us with Z1 and Z4, which on my sheet is the first choice. Might be a different choice on your test, but it should be the same answer. A reaction in which a compound breaks apart. So we start with AB and we end up with A plus B, or something that looks roughly like that. The key here is we only have one thing on the left-hand side, the opposite of synthesis, which is called decomposition. Here's a reaction. What type is it? Well, if you look at the sort of basic setup, we've got two compounds. We'll call them A and B. And on the right, we have those two compounds combined into a single reactant. We said that that is called a combination or a synthesis reaction. Either one of those answers would be correct, but combination is the one they've given us here, just different term. And this is the same question we had a couple of questions ago. When you have one substance that breaks down into two or more substances, that's the AB plus, becomes A plus B. That's decomposition reaction. If we have 1 mole of aluminum nitrate, how many oxygen atoms do we have? The molar mass really isn't relevant here because it says we have 1 mole. So 1 mole of anything is 6.02 times 10 to the 23rd molecules. So we have 6.02 times 10 to the 23rd molecules of aluminum nitrate. But the question asks us, and this we have to read carefully, the question asks, how many oxygens would there be? Well, there are, if you look here, there's a 3 inside the parentheses and a 3 outside the parentheses, which means there are 9 oxygens for every molecule. So we have 6.02 times 10 to the 23rd molecules times 9. That is 5.42 times 10 to the 24th. So that's how many oxygens there are. Okay, there's 6.02 times 10 to the 23rd molecules, but each molecule has 9 oxygens, so the total number of oxygens is 9 times as much. What is the percentage of carbon by weight in table sugar? Well, table sugar, the carbon, there's 12 of them, so carbon has a mass of 12. There's 12 of them, which is 144, and then we have the hydrogen, which is 22 times 1, which is 22, and then we have the oxygen, which is 11 times 16, which is 176. So the total mass of the compound, 176 plus 144 plus 22 is 342. So that's the total. We want to know what percentage of that is the carbon. Well, the carbon is 144. The total is 342. And then we're going to multiply that by 100 to make it into percentages. So 144 divided by 342 is 42.1%, which is this answer here. How many atoms of nitrogen are there in 49 grams of aniline dye? Well, this one's similar to the one we had a few minutes ago with the aluminum nitrate, except conveniently in this case they're asking about nitrogen. There's only 1 nitrogen per mole of aniline, so all we need to do is figure out how many moles of aniline we have and then multiply that by 6.02 times 10 to the 23rd. So we have 49 grams of aniline, and we've got 93 as the mass of aniline. So 49 divided by 93 is 0.53 moles, and then we multiply that by 6.02 times 10 to the 23rd, and we get approximately 3.2 times 10 to the 23rd atoms. What is the empirical formula of C6H12O6? Well, the empirical formula is the most simplified formula. And since all three of these numbers are divisible by 6, if we divide them by 6, we get C1H2O, which is this choice here. Again, might be a different number on your sheet, but CH2O would be the empirical or simplest formula for C6H12O6. How many moles are there in a sample that has 7.12 times 10 to the 25th molecules of Cl2? So we're going from molecules to moles, which means we're going to divide the number of molecules by 6.02 times 10 to the 23rd. And when we divide 7.12 by 6.02 with the scientific notation, we end up with 118 moles. And then if we put that into scientific notation, it is 1.18 times 10 squared moles, which is the first choice on this list. How much nitrogen gas is there if we have 48 grams of nitrogen? Well, 48 grams, so we're just going from grams to moles here. 48 divided by N2, right? 2 nitrogens would have a mass of 28. So 48 divided by 28 equals 1.71 moles of nitrogen. If we have a compound containing only carbon and hydrogen, and we know that it's 80% carbon, we know its molecular weight. What's its molecular formula? Okay, so a couple things we got to do here. First of all, if it's 80% carbon and the only other thing in it is hydrogen, we know that the other 20% is hydrogen. So first we have to find the empirical formula. When we do 80 divided by 12, we get 6.67. When you do 20 divided by 1, you get 20. So to find the empirical formula, we divide each number by the smaller number, 6.67. We get 1 for the carbon, we get 3 for the hydrogen. So that means the empirical formula is CH3. Well, if the formula was CH3, then the mass should be 12 plus 3, which is 15. The mass is not 15, it's 30, not 15. So that means that the molecular formula is twice as big as the empirical formula. Well, if the empirical formula is CH3 and the molecular formula is twice as big, it would be C2H6. Okay, if we have a formula of CH2 for the simplest or empirical formula, and the mass of the molecular formula is 70, what's the molecular formula? Well, CH2 would have a mass of 14. So mass of 14, 70 divided by 14 is 5. So the molecular formula is 5 times bigger than the empirical formula. Well, if the empirical is CH2 and the molecular has to be 5 times bigger, you get C5H10. What is the percent by mass of fluorine in sulfur hexafluoride? Well, we have sulfur hexafluoride. The fluorine, 6 times the mass of fluorine, which is 19, is 114. And then if we take 114 plus 36, we get 146. So the amount that is the fluorine divided by the total, and then we're going to multiply that by 100 to make it a percent. We do 114 divided by 146, and we get 78%, which is one of the choices, 78%. How much CH3OH would we need to react with 93.5 grams of NH3? Well, we need to figure out how many moles of NH3 that is. So NH3, which is a nitrogen and 3 hydrogens, has a mass of 17. 14 nitrogen, 3 hydrogens would be 3. So if we do 93.5 divided by 17, we get 5.5. Then we multiply that by the ratio, and it's 1 for the CH3OH, it's 2 for the NH3, which means 5.5 divided by 2, which is 2.75. And the question here asks us for moles, so that's where we can stop. If we needed to go on and do grams, we would find the molar mass of the CH3OH and then multiply 2.75 by that. But since we're asked to find moles, we can stop when we get there, which is right here, 2.75 moles. How much AlCl3 can be formed from 109.35 grams of hydrochloric acid? And again, we're given moles, or one of the choices, which is that we don't have enough information to find that, but we do. We have enough information. We have the equation, we have a starting amount. That's all we need. So we need to find out how many moles of AlCl3 we would get from 109.35 grams of HCl. So 109.35. The mass of HCl would be 36.45. One hydrogen plus a chlorine. So 109 divided by 36.45 is, we'll call it 3. It's 2.99. And then we're going to multiply that by the ratio, which is 2 for the AlCl3 and 6 for the HCl. Well, 3 times 2 over 6, 3 times 2 is 6, divided by 6 is 1. 1 mole, which is one of the answers over here. If we have 39 grams of C6H6 and it reacts with excess chlorine, which just means we don't have to worry about a limiting reactant here, we get 30 grams of C6H5Cl. What is the percent yield? Well, we need to figure out how much we should get. How much should we get if we start with 39 grams of C6H6? Well, C6H6 would have a mass of 78 grams, 6 carbons and 6 hydrogens. Carbon is 12 times 6 is 72, plus 6 for hydrogen, 78. So when we do 39 divided by 78, we get exactly 0.5. We multiply that by the ratio in the equation. It's 1 to 1, so that's easy. 1 over 1 times 0.5 is 0.5. So now what we need to know is what's the mass of C6H5Cl. Well, C6 is 72 plus H5 is 5 plus 35.4 for the chlorine. That's 112. So 112 times 0.5 is 56. So we should have gotten 56, but we only get 30. 30 divided by 56 is 53.4, roughly 53.4%, which is one of the choices. So that is the percent yield. Calculate how much you should have gotten, which is what we do with the stoichiometry boxes all the way through. And then you take that number, divide what you actually got by what you should have gotten, and you get a percentage. Just like when you get a test, you're going to figure out how many points you did get, divided by how many you could have gotten, gives you a grade, a percentage. All right, if 47.5 moles of ammonia are produced, how much calcium carbonate is produced? And we need to find grams, so that's where there's a trick here. So if 47.5 moles of ammonia are produced, well, the ratio is 2 ammonia for every 1 calcium carbonate. So we're going to do 47.5 divided by 2, and we get 23.75. That's the number of moles. The mass of calcium carbonate happens to be 100 grams. So we're trying to find the grams. 23.75 divided by, times 100 is 2,375 grams. When we round that to significant figures, we get 2,380 grams. Okay, if 14.5 moles of CO2 are produced and we reacted 34.6 moles of O2, how many moles of CH4 did we have to use, or did we use? This is kind of a limiting reactant problem. according to the equation, if we react 34.6 moles of oxygen, well, we should get half that amount of CO2. 34.6 divided by 2, or times 1/2, is 17.3. So if we used all the oxygen, we'd get 17.3 moles of CO2, but we didn't. We only got 14.5 moles, which means that the limiting reactant here is the CH4, and since the amount of CH4 that we use has to be equal to the amount of CO2 we get, that means we must have reacted 14.5 moles of CO2, or CH4 rather, to get 14.5 moles of CO2. Alright, if we react 14 moles of N2 and 48 moles of H2, we produce 21.5 moles of NH3. What is our percentage? Alright, another limiting reactant question. First, if we react 14 moles of nitrogen, how much ammonia should we get? The ratio here is 2 to 1. We should get 28 moles, right? Because there's 1 nitrogen for every 2 ammonias. If we react 48 moles of hydrogen, this ratio is 2 to 3. If it was 2 to 3, 2/3 of 48 is 36. So the hydrogen gives us a bigger number than the nitrogen does. So the limiting reactant here is the nitrogen. So we should have gotten 28 moles, but we didn't. We got 21.5 moles. So 21.5 divided by 28 means we got approximately 76.8% of our possible amount. If we react 1 mole of ammonia and 1 mole of O2, what is our limiting reactant, and then how much of the excess is left over? Well, they made this one really easy because since we have equal amounts in moles, if we were given grams, we'd have to do a little more work. But since we're given moles, all we have to do is look at the equation. According to the equation, you need 4 ammonias for every 5 oxygen. So you need more oxygen than nitrogen, hydrogen, ammonia. We don't have that. We have the same amount. So since we have less than we need of the oxygen, that's the limiting reactant, which means you can cross out all the ones that say NH3 is limiting. Now we need to know how much of the other thing is left over. Well, if we use 1 mole of oxygen, the ratio of oxygen to ammonia is 4 to 5. So we're going to use 4/5 of that amount of the ammonia, which is 0.8. The question is how much is left? Well, if you start with 1 and you used 0.8, you've got 0.2 left over. So that is the correct answer there. And then the last one is a very similar question, except they don't give us the same amount of each reactant. So we need to figure out which is limiting and how much is left over. Again, we have to do just a little more work because we're trying to figure out which one is limiting first. So 1.8 moles of NH3 compared to the 4 moles you should need gives you 0.45 as a value. 2 divided by 5 for the oxygen is 0.4. So this is the smaller number compared to how much we need. So oxygen is the limiting reactant again. This was the O2. Oxygen is the limiting reactant again. So cross out everything with NH3 as a limiting reactant. How much is left? Well, if I use 2.00 moles of oxygen, and the ratio of oxygen to nitrogen is 4/5, then that means I used 1.8 moles of ammonia. 2 times 4 over 5. So if I used, 1.6 moles. 1.6 moles. Well, if I started with 1.8 moles and I used 1.6 moles, then that means I again have 0.2 moles left over. So oxygen is limiting, 0.2 moles of ammonia left over. Okay, so make sure you know your percent composition, percent yield, how to find the limiting reactant, how to balance an equation, types of equations, how to do percent composition and empirical and molecular formulas, how to do stoichiometry, whether you're starting with moles and going to moles or starting with grams and going to grams, and how to do all the mole conversions from. Basically, you don't need to know the volume ones, but you need how to go between atoms and moles, moles and mass, and then how to get from, say, mass to moles back to atoms and do those two-step problems.